The organic pollution in wastewater is characterized by being many compounds. There are 10,000, 20,000, 50,000 different organic compounds in wastewater. This makes it difficult to characterize wastewater because it is not possible to measure each single compound in the wastewater. We need to handle the organic material in another way. There are few compounds that have a concentration where we can measure them. That can be glucose, that can be acetic acid, but most of them are in very small concentrations, and even if we measure them, we don't know how to use them in relation to wastewater treatment. So we have to take other methods into use in order to characterize the organic material in wastewater. And we have basically three bulk parameters that are being used for characterizing wastewater. There's the COD, chemical oxygen demand. There's the BOD, biological oxygen demand, and then there's TOC, total organic carbon. These three are used. BOD is the traditional way of measuring organic material in wastewater. COD is more precise and gives a better mass balance of the wastewater and the treatment process later on. And TOC is useful to characterize the type of organics that are in the wastewater. So all of them are useful in different contexts. If you look at the BOD is the biodegradable organics during 5 days. So we measure how much of the organic material is degraded in 5 days. We know that not all of this material is degraded. In typical municipal wastewater, about 2/3 are degraded during the 5 days. If we wait longer, then we will have more degradation. And we will observe degradation up to 20, 25, maybe 30 days. Then nothing more organic material will be degraded. But some of it is very slowly degradable, so it takes a long time. The reason why 5 days has been selected is that we cannot wait forever for a result to find out how is this wastewater. If we are measuring the influent to a wastewater treatment plant, it is a problem that 5 days later we get the information on how was the influent 5 days ago. This is not very useful in the day-to-day operation of a wastewater treatment plant. So that is why COD is measured by strong oxidation with dichromate, and that gives a total oxidation of the organic material in the wastewater. Another possibility is potassium permanganate, which only oxidizes part of the organic material in the wastewater. Both methods give quick results. Within a few hours you have the result, and you can use it in operation of the treatment plant and looking at what's going on in the treatment plant. But the permanganate has the same problem as the BOD, that it only measures part of the organic material. So the dichromate COD is the best to use, but it has some negative environmental impacts because there is mercury involved in the analysis. Here you can see how the BOD is measured in practice. It is a mixture of the wastewater and some pure water that is aerated, oxygen containing, and these two components are mixed in a bottle. The stopper is put on, no air allowed in the top of the bottle, and then the bottle is placed in a dark room at 20 degrees for 5 days. After 5 days, it is measured how much oxygen is in the bottle, and based on the two oxygen measurements and the mix of wastewater and pure aerated water, one can calculate how much is the oxygen consumption during the 5 days in the wastewater. The problem with this method is that there's a limit to how much oxygen can be in the pure aerated water that we mix with, so we need to have dilution series where we dilute wastewater more and more in order to have a bottle at the end after 5 days where there is some oxygen left. Because if there's no oxygen, then we cannot know how much could have been oxidized. So there must be a reasonable amount of oxygen left in the bottle after the 5 days. So this makes it complicated and expensive to make this BOD analysis. There are other methods that are more automized where the material, wastewater, is put into a bottle and the oxygen consumption is measured either after the 5 days or automatically by machine. But this is the original version of the BOD test shown here. It is important that the temperature is 20 degrees because this is a biological reaction. It is temperature dependent. And it's important that the bottle is kept in the dark, because if it is not kept in the dark, there might be growth of algae and production of oxygen, and then the whole measurement is disturbed. Here you can see how the development is for a BOD test with time and with different temperatures. As can be seen here in the middle, the 20-degree curve, that after 5 days it reaches a plateau, and that is these 2/3 of the oxygen consumption that is measured there. If we wait, in this case, in this sample here, 10 days or more, then we can see a new oxygen consumption occurring. This is not organic material. This is nitrification caused by ammonia in the wastewater, which is now being oxidized. There are not very many ammonia oxidizing organisms in the wastewater, so it takes time for them to develop a culture that is strong enough to really oxidize the ammonia in the wastewater. So this will happen after 10-15 days that this starts. In order to avoid that, it's possible to inhibit the nitrification so that the measurement only measures the organic material in the sample in the wastewater. One can see on the curves that if the temperature is higher, everything goes faster and the results are different. If the temperature is lower, 5 degrees, it is slow. So from this it is obvious that the BOD measurement is not a very accurate measurement, but it has been the traditional one, and it has the advantage that it measures what is biologically degradable or part of what is biologically degradable. And in the wastewater treatment plant, a lot of the processes are biologically, so it has a close relationship to what is happening in the treatment plant. In case of industry, the BOD can be very fast. The oxidation of organic material can be very fast. Here is an example of a curve from potato fruit water industry, and there one can see that within 2 days almost all the organic material in the sample has been oxidized, while in municipal wastewater it is a more slow process. So one has also looked into the possibility to shorten down the BOD test, but this is difficult because of the variations in the curves as shown here. So the industrial wastewater influent can affect the BOD curve. So the most safe thing is to wait 5 days and then get the result, but it is a little bit late to get the result. The COD can be calculated if we know the equation for the compound in question that we oxidize. The COD measurement oxidizes all existing carbon to carbon dioxide. Ammonia, nitrogen is not oxidized in the COD analysis. Sulfide is oxidized and can create errors if there is high sulfide concentration in the sample. So one should always observe whether there is significant amount of sulfide in the sample in relation to the measurements of COD. To calculate the COD, we need to calculate the level of oxidation of the compound, and we need to calculate the oxygen needed, which is what the COD measurement does. And the level of oxidation for the various components are so that the elements have a level of oxidation of 0, hydrogen +1, oxygen ions -2, and then a substance has a total level of oxidation equal to the charge of the substance. We can take a look or an example here for a COD calculation of ethanol. The idea here in the test is to use oxygen, so we add oxygen in the process, and first we balance the carbon, and since there are 2 carbon atoms in ethanol, we will get 2 carbon dioxide molecules out of it. And then if we have to balance the oxygen in order to end up with carbon dioxide and water, we need the oxygen shown here, that 1 mole of ethanol, 46 gram, needs 2 moles of oxygen, which is 96 gram of oxygen. So the COD is 2.09 gram of oxygen per gram of ethanol in this case. But this is more to show the basic principles of the COD, because, as I said earlier, the idea in the characterization of wastewater is not to characterize each compound in the wastewater, but for industrial wastewaters it can be useful if there is only a few compounds in the wastewater. So we will take an exercise and make a COD calculations of acetic acid, and the formula is given here on the screen. There are 2 carbon atoms in acetic acid, so we get 2 CO2, and in order to balance the oxygen we need 2 oxygen molecules. So the final result of the equation is that we have 1 molecule of acetic acid plus 2 molecules of oxygen. That will give 2 molecules of carbon dioxide and 2 water. And the molecular weight of acetic acid is 60, and it needs 64 gram of oxygen. So the COD of acetic acid is 1.07 gram oxygen per gram acetic acid. The COD we have in wastewater is not just 1 compound, as we have talked about earlier. It consists of many compounds and has different grades of degradability. So it's important to fractionate the COD if we move into nutrient removal processes where the detailed COD composition is important for the success of the nutrient removal processes or for the design of the processes. This figure shows an experiment where activated sludge is loaded with wastewater for 12 hours between hour number 2 and hour number 14. At the same time, we have measured the oxygen consumption, grams per cubic meter per hour. As you can see, before the addition of wastewater, there was an oxygen consumption, an OUR, of between 15 and 20 gram. When we begin to add wastewater, the oxygen consumption increases, and over a few hours it ends up with a plateau about 40 gram of oxygen per cubic meter per hour. This is rather stable until we stop the addition of wastewater, and what we observe then is that we have a drop immediately in the respiration. And then we have what is called a shoulder, where the respiration slowly decreases down to the level it had before we added the wastewater. What do this curve tell us? The drop we see after stopping the addition of the wastewater shows us the easily degradable part of the COD, which is oxidized almost immediately when added to the activated sludge tank. And the moment we stop the wastewater addition, then the respiration related to this part of the organic material stops, and we have this drop. So from this curve we can get an idea of the amount of very easily degradable COD in the wastewater. This is a COD part which is very valuable in nutrient removal processes because it gives fast processes this easily degradable COD. It can be used, most of it, almost directly by the microorganisms, so the metabolism is fast. If we look at the curve, the shoulder curve with a slow reduction in oxygen consumption, what is happening here is that we have material which is more slowly degradable. It can be mainly particles, but also some soluble material in the wastewater. They need to be hydrolyzed. It will take time, so they degrade slowly, and the result is that we get this change in respiration over the next 12 hours in this case. From this we can see some rates that we can obtain in the wastewater, and from the shoulder shape we can analyze more details about the composition of the COD. So it is important in nutrient removal processes to make analysis of the COD fractions that we have. They can be done in many ways and many ways of characterization. If we have here a COD of 500 gram per cubic meter, we can see what happens if we do various analytical activities on this COD. We can filter it with different types of filters shown here, and we will then have a COD of something like 200 gram per cubic meter that passes the filters. And if we filter with a very narrow opening in the filter, 0.22 micron, we get something which is about 200 gram soluble COD. But the other concentration, 220, is also soluble COD, so there's no clear definition of soluble. It depends on the filter size. We can use molecular sieves that lets us pass materials with molecular weights of 10,000 or 1,000. Geofiltration. We can measure the VFA, the volatile fatty acids in the wastewater, and that will typically amount to maybe between 5 and 10% of the total COD. We can measure the carbohydrates, which will be not much, but maybe 15. Proteins a little bit more. The BOD will typically be around 200 to 250 in this COD. And then at the bottom we have a splitting of the COD based on the fractionation, where we can see the inert COD. There is part of that which is suspended, which is at the right side of the curve, and there's also soluble inert COD, approximately 10 in this case, which are the part of the soluble COD that cannot be degraded. The suspended COD inert is 90. If we look at the remaining part of the COD which is degradable, we have the very easily degradable part, which in this case is about 100 COD, and we have a part which is easily to hydrolyze, also 100, and then we have the slowly degradable, slowly hydrolyzable COD, approximately 200. So this detailed investigations will help us in analyzing the possibilities for nutrient removal processes, either for phosphorus, biological phosphorus removal or nitrogen removal.